let's just say we have a reaction where A is at equilibrium with B. So remember that when reactions are at equilibrium, the concentrations of your product and the concentrations of your reactant, they remain constant, because as A turns into B at a certain rate, B turns back into A at the same rate. So if the rates are equal, well, the concentrations have to be constant. Now you can see in this diagram, the concentration of A is 0.4 molar. Concentration of B is 0.2 molar. Now, if we wanted to write out the equilibrium constant for this reaction, let's say this reaction is at some temperature. Let's say this is at, I don't know, 300 degrees Kelvin. Just doing a random temperature. But the equilibrium constant, remember, that's going to be the concentration of your products raised to their respective moles. So in this case, there's only 1 mole of B, so I'm going to raise this to the first power. And this is going to be divided by the concentration of the reactant raised to the mole. So there's only 1 mole of that, so it's to the first power. So in this case, my equilibrium constant, that's just going to be 0.2, right, because that's the concentration of B, divided by 0.4, because that's the concentration of A. And that's just going to be 1/2, okay, or 0.5. Now, let's take a look at what happens if I increase the concentration of A. So let's say what I do is, in whatever container I have, I dump a bunch of A into whatever container I have, and like I increase the concentration of it. So let's say this new concentration that I have is 0.8 molar. 0.8 molar. All right. So I increase the concentration of A. Now, what do you think is going to happen? All right. When I increase the concentration of A, notice how actually if I write out the reaction quotient for this reaction. So remember, equilibrium constant, you only write it when the concentrations, these are like the concentrations at equilibrium, right? So 0.2 is the concentration of B at equilibrium, 0.4 is the concentration of A at equilibrium. However, once we're out of equilibrium, once we're not at equilibrium, we have to use sort of the reaction quotient to compare it to the equilibrium constant. So if I write out the reaction quotient, it's the same expression for the equilibrium constant. It's going to be the concentration of B divided by the concentration of A. So in this case, the concentration of B, well, my new B value is 0.8. Divide that by the concentration of A, which, the concentration of B is 0.2. The concentration of A is going to be 0.8. 0.2 divided by 0.8 gives me 1/4, or 0.25. Notice how the first thing that I notice is that the reaction quotient is not equal to my equilibrium constant at that temperature. And that implies that, well, my reaction is not at equilibrium, right? Because the relative ratios are different. In addition, notice how QC, my reaction quotient, is less than equilibrium constant. And this basically implies that, well, if QC is less than KC, well, think about it, right? In order for this number, this equilibrium, this reaction quotient to be less than the equilibrium constant, well, what has to happen is that we have to have a big denominator. All right, because remember, if you have a big denominator, well, you're going to get a smaller value, right? If you have a big denominator, you're going to get a smaller value. And what's in the denominator? Well, reactants, right? My reactant is in the denominator for writing out the equilibrium constant expression. So kind of when QC is less than KC, remember that this means that, we have a lot of reactants. We have a lot of reactants. And therefore, what's going to happen to this reaction is it's going to shift to the right because we have too many reactants. So what's going to happen is all those reactants are just going to start reacting with each other, right? If we add more reactants, they're all going to start hitting each other, and there's going to be more reactions that happen. So this sort of reaction is going to shift to the right because there's going to be sort of more collisions going on with A, right? Since you add more. Now, let's say this reaction restores equilibrium. So after this time period where, I add more A, well, let's say this reaction restores equilibrium. So if the reaction shifts to the right, well, what's going to happen? You're going to be losing some of your reactants, right? Because they're reacting, and you're going to be gaining some products. So it makes sense why the graph kind of looks like this. Now, let's say at equilibrium, the concentration of A at equilibrium, once again, let's say that's equal to 0, or let's just say that's equal to 2/3. And let's say the concentration of B, right? The concentration of B, let's say that's equal to 1/3. So at our new equilibrium, notice how the concentration of A and the concentration of B, they're completely sort of different values than what we started with, right? Than what we started with. So if I write out the equilibrium constant expression, something weird happens, all right? Let's say I write out the equilibrium constant expression once again, because now that I've restored equilibrium, I can write out the equilibrium constant expression because these are the concentrations at equilibrium. Remember, only use equilibrium constant if you have the concentrations at equilibrium. So in this case, remember that equilibrium constant for this reaction is concentration of B over the concentration of A. What's my concentration of B? 1/3. Sorry, it's 1/3. What's my concentration of A? 2/3. 3's cancel out, and you get, wait, what the hell? You get 1/2, which is 0.5, which is exactly what I started with. So notice how when you actually change the concentration, you actually don't change the equilibrium constant. Okay. Remember, the only thing that changes the equilibrium constant is the temperature, and I will be talking about that in this video. All right. The only thing that changes the equilibrium constant is the temperature. But other than that, pretty much nothing else changes the equilibrium constant because remember, the reaction is just going to shift back to equilibrium, and basically the relative ratios of the products, the reactants, they're going to remain the same. All right. They're going to find some way to restore that. Now, this is kind of a review of Le Chatelier's principle. Let's say if we have a reaction where A, which is a gas, turns, actually, let's make this, all right, so let's say 2B, and then make this gas. Okay. Let's say if we have a reaction where A is at equilibrium with 2B, and both of these are gases. So all of these are gases. So this is A. Let's say this is turning into 2B. Now, let's say that I increase the volume of this container. All right, so wherever the gas particles are located in this container, I'm increasing the volume. What's going to happen? Well, increasing the volume is the same thing as decreasing the pressure. Because when you increase the volume of the container, it's going to take longer for your gas particles to hit the walls of the container. So the pressure is going to be lower, okay? Let's just say originally, in my original box, I started out with a pressure called P1. And let's say I increase the volume. So if I increase the volume of this container, let's just call this new pressure P2. Notice how P2 is actually going to be less than P1, right? Our new pressure is going to be less than our original pressure because our box is bigger. It's going to take longer for the gas particles to hit the wall. So I want to find some way to restore pressure, right? I want to find some way to make P2 equal to P1. I want to make these pressures equal. So how do I do that? Well, my reaction is going to shift to the side with the most amount of gas particles. The more moles you have of gas particles, the more pressure, right? Kind of makes logical sense. So my reaction is going to shift to the right, to the product side, right? In order to make the pressures equal. And likewise, if I decrease the volume, then that's the same thing as increasing the pressure. And as a result, my reaction will actually shift to the left. Because if you're increasing the pressure, then, well, let's actually do it on another container. Let's just say this is P3. Because my container is smaller, it takes gas particles less time to hit the walls. So my pressure is in this container is actually going to be greater than my original pressure. And, I want to make these pressures equal to each other, right? So how do I do that? Well, I have to find some way to decrease the pressure in this container. And how do I decrease the pressure? My reaction will just shift to the side with the least amount of gas particles. Which side has less gas particles? The product will shift to the reactants because the reactant side only has 1 mole of gas. Product side has 2 moles of gas, right? So it's going to shift to the left. Now we can talk about temperature. How temperature sort of changes. We talked about how this changes K, the equilibrium constant. And we're also going to just review Le Chatelier's principle. Now, remember that the change in enthalpy for a reaction, remember that a change in the enthalpy for a reaction just kind of tells you kind of the heat of the reaction, right? If it's absorbing or if it's releasing heat. If delta H is negative, that means that you're releasing heat, and therefore the reaction is exothermic. So if the reaction is releasing heat, right, let's just say like you light up a match, right? A combustion reaction. That's going to be releasing heat. So when you get close to the match, it's going to feel warm, right? Because it's releasing heat. If your change in enthalpy is positive, you're absorbing heat. And this reaction is called an endothermic reaction. Now, let's say if we have A reacting, is it reacting? Do I want to make it react with anything? Nah, let's keep it simple. Let's say if we have A and that's at equilibrium with B. And let's say that my change in enthalpy is negative 300 kilojoules per mole of reaction. Should probably say mole of reaction. I mean, in this case, one mole of this reaction just represents like the original reaction. If I have 2 moles of the reaction, that essentially implies that I have 2 moles of A in this case. That's at equilibrium with 2 moles of B, because I have twice the amount of stuff, right? My change in enthalpy is actually going to double. The change in enthalpy for this reaction is actually going to be 600 kilojoules per mole of reaction. Right, so you kind of get the gist there for the mole of reaction part. Anyways, yeah, so like moles of reaction pretty much just kind of tell you like the reaction progress essentially. Like if you have 2 moles of reaction, well, you're going to get 2 times the amount of sort of products that form in some reaction, right? So yeah, let's just say that this is occurring at 300 degrees Kelvin. Let's say this reaction is occurring at 300 degrees Kelvin. And let's say you increase the temperature to 400 degrees Kelvin. So which way will the reaction shift? Well, I can sort of rewrite this reaction as A is at equilibrium with B, and I'm going to put a plus heat at the end. Now, if we take a look at the delta H sign, notice how it's negative, meaning that we're releasing heat. So heat can be treated as a product of this reaction. Now, if we're increasing the temperature, we're essentially increasing the amount of heat there is. And if we treat heat like a product in this case, we're increasing the concentration of a product. That's going to shift my reaction to the left. And likewise, if my delta H was positive, well, that would imply the opposite, pretty much. All right, if my delta H was positive, that means I would have a plus heat at the front, right? Because it's absorbing heat. So if I increase the temperature, I'm increasing the amount of heat. My reaction will shift to the right in this case. All right. Now, changing temperature changes the equilibrium constant. And this is something known as the Van Hoff equation. Okay, so this is an equation that sort of relates a change in temperature to a change in the equilibrium constant. So let's take a look at this example. So, I mean, the formula is ln K2 divided by K1. And then this is going to be equal to negative. I'm just going to write this all out. All right, so this is going to be the Van Hoff equation. So you have ln of the second equilibrium constant divided by the first equilibrium constant is equal to negative delta H naught divided by R. R is a constant. And then this is going to be times 1 over T2 minus 1 over T1. Now, this equation seems very complicated at first. But what you have to realize is, notice how this reaction has T1, T2. So T1, T2. And notice how it has K1 and K2. This equation gives you the relationship between changing temperature and changing the equilibrium constant. But remember that we also have to take into account if the reaction is exothermic or endothermic, right? Because of this delta H we have in the front. Remember, the previous example, right? Depending on your delta H value, that kind of determines which way your reaction will shift. All right, let's do a practice problem. So actually, one more thing, in case you guys don't know what this knot is, you might have heard this phrase before. When people say like something is at STP, that kind of just means that the reaction is at 0 degrees Celsius, right? And then the pressure is at 1 atm. So it's used as sort of like a basis of comparison for like reactions. Now, this is something known as the not symbol, and it represents. I'm gonna write this down first. But this pretty much represents the standard state represents sort of a set of sort of conditions. All right, a set of conditions. So usually the pressure is at 1 bar. The pressure is at 1 bar. The concentration, if you're dealing with solutions, that's 1 molar, and temperature is usually 25 degrees Celsius. Or I'm pretty sure 298 degrees Kelvin. But these are basically like the standard conditions, right? These are conditions that are used as like a basis of comparison. Okay. All right, so let's say if we have a reaction where A is at equilibrium with B. So let's say that when my temperature of this reaction is 298 degrees Kelvin, my equilibrium constant is 1.00 times 10 to the negative 3. Remember, equilibrium constant has no units. Let's say if I increase the temperature to be 350 degrees Kelvin, so that's my T2, right? What's my new equilibrium constant going to be? And one more piece of information is that this reaction has a delta H naught of 50,000 joules per mole. Remember that because my delta H is a positive sign, that means my reaction is endothermic. Now, kind of just basing it off of kind of this reaction right over here, if I increase my temperature, that's the same thing as increasing the heat of this reaction. Therefore, my reaction will shift to the right. So that means that the amount of products I have is going to increase, right? The amount of products that I have is going to increase. Now remember that when I write out my equilibrium constant, right? Remember it's products over reactants. So in this case, if I'm increasing the amount of products I have, I'm kind of expecting that my answer for K2 is going to be greater than what I originally started with. Because if I'm increasing the amount of products is in the numerator. So I'm expecting that my equilibrium constant increases for this K2 right over here. That's just a prediction though. Let's actually do the calculation. So if I plug all of these values in, and remember that R is just a constant, right? R is just a constant. So if I plug all these values in, I'm going to get. So this is what I get when I plug all the values in. What I can do now is I can raise both sides to the E power. E and ln cancels out, and I just get E to all of this right over here. And if I want to solve for K2, after this step, what I can do is, so let me erase the E and ln because they cancel out. After this, what I can do is now I can just multiply both sides by, 1.00 times 10 to the negative 3, right? Because now, I'm just going to multiply this by, I know this is a little sloppy, I'm sorry guys, but it is what it is, right? And this and this cancels out, right? So I'm just going to be left with K2 as the final thing, right? I isolated my variable. So K2 is equal to 1.00 times 10 to the negative 3 times E to the, and then blah, 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 blah. Putting this into my calculator, let's see what I get. All right, I just put this in my calculator, and I got a 0.02 as my answer for the new equilibrium constant. So, all right, so going back here, I put 0.02. Actually, I should probably round to 3 sig digs because I started out with 3. Actually, nah. This 50,000 only has 1 sig dig, so I'm chilling. All right, but anyways, this right over here can be written as 2 times 10. Actually, 2 times 10 to the negative 2 power, negative second power. All right. Now notice how once again the equilibrium constant has changed, first of all, right? So this kind of confirms our idea that changing temperature kind of changes the equilibrium constant. But also notice how my equilibrium constant has increased. And this is just like what I predicted, right? Just writing out my reaction, I can predict, whether the reaction shifts to the right or the left based on my change in enthalpy. And based off of that, I can make predictions about my new equilibrium constant. And I supported that with my calculations as well. Let's finally talk about the effects of a catalyst. All right, catalyst. Now, let's say if we have a reaction at equilibrium, once again, I'm using the same reaction. A is at equilibrium with B. But let's say that I have addition of a catalyst. So what do you think a catalyst does in terms of kind of the rate of reaction? Well, what catalysts do is they lower the activation energy for a reaction, and therefore they increase the rate of a reaction. But the thing to note is that catalysts actually don't change the equilibrium position. So if a reaction is at equilibrium and you add a catalyst, the reaction is going to stay at equilibrium. It's not going to shift to one side or another. And I think the best way to kind of visualize this is to use a potential energy diagram. So on my y-axis, I have potential energy, and on my x-axis, I have pretty much just reaction progress, something like that. Reaction progress. Notice how for activation energy for the forward reaction. I don't have any space, so I'm just going to write it here. And then this right over here represents the activation energy for the pretty much the reverse reaction. All right. So let's say that on the left side right over here, I have A. Now, in order for A to react, right, it has to overcome an energy barrier, and that's basically called the activation energy for a reaction. Right. This is the reason why, in order to light up a match, you gotta like take the match and you gotta scrape it on the side of the container. That gives it the initial boost of energy it needs for the reaction to happen. Now, notice how this reaction is also reversible. So maybe on my x-axis, I shouldn't say reaction progress because it kind of implies. I mean, does it work? Yeah, I think it works. Yeah, I'm tweaking a little. All right. Anyways, in order for B to turn back into A, because remember this reaction is reversible. So when A turns into B, B also turns back into A. So in order for B to turn back into A, notice how B has to overcome a bigger activation energy, right? A bigger activation energy in order to turn back into A. However, because this reaction is at equilibrium, the rates of the reaction is the same. So at the same rate, A turns into B, B turns back into A. Now let's say if we add a catalyst into the reaction. What a catalyst does is it provides an alternate reaction pathway, and therefore it lowers the activation energy. So now, with the addition of my catalyst, notice how my new activation energy for the forward reaction is represented by this green arrow, right? So my new activation energy is going to be this green arrow right over here, right? I lowered the activation energy. But notice how for the catalyst, I also lowered the activation energy for the reverse reaction, right? So when I add in a catalyst, not only does that lower the activation energy for the forward reaction, it also lowers the activation energy for the reverse reaction, right? Because now B can just go up right over here. This green arrow right over here basically represents my activation energy for the reverse reaction. And notice how it's smaller than what it originally was up this hill, right? So because catalysts change, so let me just write that down. Because catalysts change the activation energy of the forward and the reverse reaction, it actually has no change on the equilibrium. All right, so because catalysts, they change the activation energy for the reverse reaction and the forward reaction, it actually does not affect their equilibrium at all. The reaction will occur at a faster rate, but it's going to be a faster rate for both sides, if you know what I mean, right? So remember, catalysts, they increase the rate of a reaction, but in this case, because they affect the forward and the reverse reaction, it increases the rate of reaction for both sides. So it kind of like cancels each other out, if you know what I mean, right? It doesn't have an effect on the equilibrium position.